All right, let's look at this problem called the k weakest rows in a matrix. All right, so you're given a ampersand binary matrix of ones and zeros. Okay, ones are soldiers, zeros are civilians. Soldiers are positioned in front of the civilians. That is, all the ones will appear to the left of all the zeros in each row. So, for example, in this matrix, we first see all ones and then we see all zeros. So the matrix only contains ones and zeros. Each row first has all ones, then it has all zeros. What do we have to find? A row I is weaker than a row j if one of the following is true. Number of soldiers is less than the number of soldiers. Okay, so in this case, a weaker row is the one which has less number of soldiers. So this is the weakest row. It has only one soldier. And if the soldiers are same, then it's just a row number. So in this example, we find the number of soldiers in each row, and we can see this has the smallest number of soldiers. So row number 2 is the smallest. And after that, which is the next smallest row? There are two with the same number of soldiers. So we go with row number, so 0 and 3, and then 1 and 4. So we have to find the k weakest rows, not all, just not the all the rows, just the k weakest rows. In this entire sorting is this, but we only have to return, because k equals to 3, we just have to return 203. All right. So there are a few things here. First, how do you find the number of soldiers in each row? Right? We can do binary search. Right? There's only ones and zeros. We can do binary search to find the number of ones. That is one. What else? Then you have to find the k weakest rows. So we can find the number of rows like this, number of soldiers in each row, and then we can do a sorting on it uh, based on this logic, where the smallest one is the one with the smallest soldiers, and if the number of soldiers are equal, then the smaller one is the one which has a smaller row. We can build a logic for sorting based on that, and then we can sort it. The other bit is, so let's talk about the time complexity first before even solving it. So for each row, what are we doing? First, for each row, we are finding a number of this, right? A number of soldiers, which will use binary search, so log n, m cross n is a matrix. So that is fine. So m log n is needed, the time needed to uh, get this. But now if you sort it, uh, sorting will take m times log m, and then you just return uh, the first k elements from the sorted list. Now you can improve this a little bit by, instead of log m, you can do it log k by using a priority queue or something, right? The top k elements, instead of the array, you can use a priority queue. And because priority queue will only, um, you will add all the elements in the priority queue, but you will not allow the priority queue to grow more than size k. So you're only interested in k. So that is why how you can slightly reduce. So let's sort of understand how all of this works by writing the code directly. The first thing what I want is this. I want to know number of soldiers given a row, right? So number of soldiers in this array. So we know this array is contains first all ones and then all zeros. So let's define L as 0, or as, and number of soldiers initialized to 0. Now what we do is while less than equals to R, look at mid L plus or minus L by 2. If this is 0, that means you're somewhere in this right side, you are not even reached to the soldier side. So you want to go to the soldier side, and you can go by doing R equals to minus 1. And if it is a soldier, then what do you do? Well, if it is soldier, then this is my potential last soldier, right? So if I reach, that means at least the number of soldiers are at least whatever index I am at, mid plus 1. At least these many number of soldiers are there. Like, for example, when I'm at here, this will be my mid. So I'll say the number of soldiers are at least 3, and then I'll move on further to look at the right side to see if there are more soldiers on the right side. So L equals to mid plus 1. And if you find more soldiers on the right side, right, then that will override. So for example, if I go here, I'll say my left equals to this and my right equals to this, right? So now when I'm looking at this, my mid will be this, and again mid will be 1. So now this will become, the number of soldiers will become um, this much. And then I look at further here, and it's 0, 0. So nothing will happen. So I'll come back to here, and so my L and R both was here. Now my R will shift back. This condition will be broken. So the last time when I said this is actually the number of soldiers, right? So that makes sense. So this is it, and then you return the number of soldiers. So this is the binary just to find the number of soldiers. Now, how do we save this number of soldiers? So let's do this. Soldiers equals to new int array of size 1 for I equals to 0 and plus plus. So now you get soldiers of I equals to number of soldiers in this row, right? So you get this. Now what do we do? Now we add into the priority queue. So now, or one thing we can do is we can sort, and we can maintain both the row number and the column number, and we sort based on that, or we can just use priority queue. So let's add. So okay, so what I'm doing in, I'm using priority queue to find the smallest k elements, right? So how do I find how do I use priority queue to find the smallest k elements? I keep adding to the priority queue, and when my priority queue size becomes k, then which element will I want to remove? I want to maintain the smallest k elements, so I want to remove the largest elements so far that I've seen, right? Because I want to remove the largest elements that I've seen so far, I'll maintain a max priority queue. Okay, so if I keep a max priority queue, and whenever my priority queue size becomes greater than k, I'll remove the largest element. So at the end of the day, what I'll be left with is the smallest k elements in the descending order, right? So I go priority queue, integer. Okay, but now we have to figure out how we add the comparator. Uh, so A and B, if it's given, first you want to look at the number of soldiers, right? So if the number of soldiers are equal, what do we do? So um, soldiers of A, if they are equal, just B, if they are indeed equal, then what do you return? Then you return just B minus A. Okay, you're doing max, right? So instead of A minus B, we are doing B minus A. That's just the row number. Else we do soldiers. So we do soldiers B minus C. So that's how the logic of the max priority will be. So now what we're going to do is we go through each row. So for int I equals to 0, less than length plus plus priority queue dot add I, and the logic would be this. And if at any point in time the priority queue size is greater than k, then you remove the largest element. Because it's the max priority queue, the largest element will be removed. So at the end of all of this, I'll have a max priority queue which will have the uh, smallest k elements, and at the top I will be with the kth, like so 1 to k. At the top will be the k. Now I want it in descending order, right? So what I do is, so basically what I mean is, let's say the top 3 elements are, um, it will be some, it will have, because it's max priority, it will have something like this, but I want to show it in 1 2 3. So I'll put this at the end of my result. And how do I want the result to look at? It's just an integer. Okay, so integer result is to new integer array of size k, I equals to k minus 1, I equals to 0, I minus minus, and you do result of I equals to priority q dot. Okay, and then you return the result. All right, let's run. and see if there are any compilations. If there are, line number 59, line number 61. Let's go to, okay. Run again. Runtime error, let's fix that. Number 2754. This is 27. Result of I speaker.poll. Hmm. Okay, it says the priority queue poll value is coming as null for some reason. Let's understand why that's the case. Oh, because of this mistake. I less than so this is long. Okay. Let's fix any more errors if there are. Okay, it works. Let's submit and see if all the test cases pass. It does, and it gives a good time complexity and space complexity as well. Let's talk about the time and space complexity once again. So what are we doing here? We are going through the number of rows, which is m, and for each of them, we are doing a binary search, right? So this is m log n, and then we are building a priority queue of size k because inserting element into the priority queue at max will take log of k because you're not allowing it to get bigger than k. So this is log k, and we are doing this how many times? M times, right? So this becomes what? M times log k. So your overall time complexity becomes what? M log n plus m log k, which is sort of equal to m log n, or I don't know. But yeah, no, it doesn't not necessarily. Depends how much k. So you can define it just like that, and it's good. What's the space complexity? Well, m, because we're using this space, uh, we're building this priority queue of size k. We're building this space of size m. So m plus k, right? So the space complexity is m plus k. All right, that's it.